Sample problem 4.1 involves using molecular scenes to depict an ionic compound in aqueous solution. And previously we've talked about in Chapter 4 strong electrolytes, weak electrolytes, and just electrolytes in general. And this tells us that the beakers shown below contain aqueous solutions of strong electrolyte potassium sulfate. And a strong electrolyte is something that completely dissociates in water, right? This term, aqueous solution, lets us know. Anytime you see that term, that means that these things are going to be in water. So let's see here. Which beaker best represents the compound in solution? For A part, and it says H2O molecules are not shown. So the first thing I want to do is I actually want to write the formula for potassium sulfate. So from the periodic table, potassium is going to have a +1 charge. So let me go ahead and write that up here, potassium with a plus charge. And then sulfate is SO4 with a 2 negative charge. So our formula then will be K2SO4. So for every 1 sulfate, I have 2 potassiums, right? Because this has a 2 negative and this has a +1. I got to have 2 to cancel out that 2 minus. All right, so let's see. A has 1 sulfate, right, with that 2 negative charge, and 2 potassiums. B has 1 sulfate for every 2 potassiums. C has 1 sulfate for every 2 potassiums. And D has, let's see, so it can't be D if you notice, right? It has 2 sulfates for every 1 potassium. So I'm going to immediately put an X through D. It can't be that. Now notice this said that it was a strong electrolyte, right? Strong electrolyte. That means it should be completely dissociated. So A has the potassium sulfate still bound together, so I'm going to immediately cross out A. B also still has some of that going on, right? If you look here on B, it still has one of the potassiums attached to the sulfate. So the only one that it could be for A, right, is the picture depicted in scene C, where it has it completely dissociated. And there's 1 sulfate for every 2 potassium, so it's got to be C. B part says if each particle represents 0.1 mole, what is the total number of particles in the solution? All right, so each particle, let's count the particles. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah. So we have 9 particles there. So I've got 9, and each particle represents 0.10 moles. So that means I'm going to have, let's see, 0.90 moles of particles in that scene. All right, and notice it's asking for the number of particles. So I now know how many moles of particles I have. And if you'll remember, Avogadro's number tells us how many particles are in each mole, so I'm going to have to do a conversion here. So let's see, I've got 0.90 moles. And I'm going to set up my T, and if I've got moles in the top, Avogadro's number tells me that for every 1 mole, right, that has to go on the bottom, there's 6.022 times 10 to the 23 entities, and here I'm going to let my entities be particles since that's what the problem's talking about. All right, so let's see what that equals. 0.9 times 6.022 times 10 raised to the 23, and I got 5.42, that's going to round up, times 10 to the 23 particles. Okay.